All right, good. So Siqi will teach us some high-dimensional expander stuff.
Cool. Thanks. So yeah, today I'm going to talk about Coboundary and Cosystolic expansion. So as Avi was saying, this is kind of a generalization of expander to like simplicial complexes. And I think many of you may be at Yotam's talk a couple of weeks back, where he talked about like the spectral generalization of high-dimensional expander. Today, this notion, I need to say that they're actually different and not really equivalent. So this is something, yeah, just something to keep in mind. And this more specifically generalized edge expansion instead of like spectral expansion. Okay, so as I'm writing underneath this board, I just want to quickly just recall what an edge expansion is. And later we can see how the formula for like the so-called coboundary expansion actually just generalized this like condition in a very nice way. So an edge expansion for a graph is defined as following. So we define this quantity to be basically the conductance of the graph. So that is basically saying like for all proper subsets of vertices, we have that the edges exiting the set in the graph over the total number of vertices in this set normalized carefully is greater or equal to some constant. So it means like most of the adjacent edges of a subset. Oh, that's fine. Most adjacent edges of a subset basically goes outside the set. So that's the main expander. Okay, so I hope this is clear. And but I want to write maybe this condition in a slightly convoluted way. Probably not strictly necessary for graphs, but will make it easier for us to generalize later. So instead of thinking about sets S and the cuts between S and the complement of S in the graph, I would like to define this as a function. S, like an indicator function of the set S, which maps vertices to 0, 1. And I would also identify this edge set with this indicator function of the cut between S and S complement. Okay, so I like to talk about functions instead of edges. And we also define a set of all functions over the vertices, which we denote by C0, and it's called cochain. So don't worry about the name, but basically just is a collection of all functions from V to F2. And also we analogously define a set of all functions from edges to F2. Okay. And next thing we want to define is an operator, but the coboundary operator, which maps functions over C0 to functions over C1. So maybe you can already guess what kind of map I'm aiming for. I'm exactly aiming for those that will map the indicator of S to the indicator of the cut between S and S complement. So, so I guess just to write it more explicitly, okay, if I have delta applied to a function f over vertices, and now I evaluate it over an edge, it will be equal to, well, actually, I don't need this. It is equal to fu plus fv. Okay, so very simple. And maybe I just want to make 2 comments. Like one can equivalently think about these functions as like basically vectors over f2 to the v and vectors over f2 to the e. So we're all thinking of finite dimensional things. So because of this identification, we can also view this delta as a function in f2 to the, I think, e cross v. And it exactly encodes the incidence matrix between the vertices and the edges in the graph.
So in general, F2 can be any field. You will specify everything with F2 because usually there is a minus there for
Yeah.
the matrix.
Yeah, that's right. Actually, in general, it could be any group, not even just field. But yeah, we care about F2 because it's really analogous to like what's going on in the edge case. Yeah. So okay, so this is the amount that we'll talk about on the graphs. So next, we'll talk about what's a d-dimensional simplicial complex.
F2 is special because it captures cuts, right? This is like something very special about.
Yeah, I guess there are other things that have other interpretations. Actually, I need to acknowledge, I think Newton told me that if one replace F2 with some symmetric group and stuff, one can view this view functions as like view certain subclasses of functions as ways to lift this this simplex to larger cover. So I guess even other choices also have other meanings. But yeah, this one is closer to edge expansion. Yeah. Okay. So so we want to generalize this notion to more higher dimensional graphs and specifically to like simplicial complexes. So a d-dimensional simplicial complex is a hypergraph, which I denote by chi. So it's a collection of vertices, which we usually write chi0, and the edges and up to chi d. So I guess a couple things to notice, like these are just the vertices and these are the edges, and these are like a hyperedge of cardinality d+1. So in general, chi I is a subset of chi0 choose I+1. Okay, and also simplicial complex have the property of close down. So if a specific, okay, so more conventionally, we don't call them hyperedges, we call them faces. So these will be zero faces, which are vertices, and one face are edges, two faces are triangles, so on and so forth. So property says that if S is a I face, then all subsets of S are also inside this simplicial complex. So this is the close downness. And the second thing, which I think sometimes we just kind of assume, but I feel maybe it's better to spell out here, is that all edges or all like faces, all I faces belong to some face R that's inside chi. So that is to say, like basically the top level face are like of every, okay, the top level face basically defines the entire simplicial complex, because every single like smaller faces comes from a large, like a D face basically.
Siqi, can you write just a bit bigger for the Zoom and the,
Oh, right, okay.
and also for the recording? Yeah, no, from now on.
Okay, yeah, okay, sorry, I did not, okay, I will do that. Okay, so this is simplicial complex. And now to define like coboundary expansion, we are going to do what we did there. Like we have like basically these like these function spaces. So they're really called the chain complex. Do you think this is?
Yeah, that's great.
Chain complex. Okay, so for every simplicial complex, we can define the chain complexes. So these are just the space of all functions from I face to F2. Okay, maybe I think instead of writing starting from 0, I will start from I-1, Ci, and Ci+1. They're set before and so similarly as before, I guess we want to define operators between them so that we can talk about things like cuts. So we call this one delta of I minus 1 and this one delta of I. These are co-boundary maps between these classes of functions, spaces of functions. Okay, so I guess you guys could probably already guess how these are defined. These are still like induced by the incidence graph between I minus 1 phase and I phase and I phase and I plus 1 phase. So I think a more interesting thing to note here is that if I compose two consecutive co-boundary maps, so if I have, let's say, a function f, it's like this, inside Ci minus 1. So if I apply delta I minus 1 and delta I to f twice, and now it becomes a function in this space. The claim is that this is actually the constant zero function. Okay, I think I should probably just quickly write why that's the case, but I think it's a very simple calculation. So what's going on is, let's say, maybe for ease of notation, I will denote elements in I minus 1 just v, and elements in I just e, and the I plus 1 faces by t. So it's like a vertex and triangle. Okay, so basically, so if we evaluate this function over t, then that's essentially equivalent to first evaluating this function over all edges in t. So
not the delta I and delta I minus 1 result.
So actually, I think because I'm applying operator from the right, so this will be a function inside Ci, and I apply this again, it will be a function inside Ci plus 1. Yeah, I'm applying from this direction. Okay, so if I treat, so what I should think about is I should treat this as a function as in Ci and think about what does it mean to apply this co-boundary operator to this function Ci. So it will be equivalent to like having basically applying this function over every e inside d. And we further look at how to open up this function. So this is equivalent to summing over all v inside e f of v. So I mean, everything is unordered in what I'm considering. So maybe this is something I kind of skipped when I'm saying it. So what it means is that every fv will be considered actually twice, because there are two ways of getting fv. You can get it by, like, if t is equal to v union, let's say some element e1 and e2. Oh, okay, e is a bad notation. Maybe a1, a2. Then I can get v by first removing a1 and get an e, and then removing a2 to get v. Alternatively, I can also first remove a2 and then remove a1. So every fv actually appears twice in the summation. And since we're doing operation over f2, this will give us a 0. So, so I guess what all this is saying is that Ci minus 1, its image under this co-boundary operator is contained inside the kernel of the next operator, delta I. Okay, and we actually give names to these two spaces. This we call co-boundary. because it's an image of coboundary map. And this we actually call, oh, actually, sorry. It should be VI. So the convention is that, well, I guess the convention is that because these are functions in CI, so they will all have index I here. So BI will be coboundary and the ZI will be cocycle. Okay, so
These are also functions in CI. CI are also functions.
yeah, they're all functions. They're all functions in CI. I guess so far we are not touching much on examples, so I want to get a bit concrete next. So the very specific case, in case of I equal to 0, this is the case we know the best because I equal to 0, these are all functions over like C0, which are just the indicator functions of sets, vertex sets. So this is a case we understand the best. So we want to interpret basically these BI and ZI in this setting. Okay, so what is B0? So I guess, okay, might be a bit strange because it seems like we have to have a C-1 to define what's a B0. So we actually can create a C-1. If we think about having an empty element in our graph, okay, basically Ci-1 is just all functions from null to F2. So there are just two functions here, and we can define, okay, its image. B0 being its image would be like delta -1, C -1. It would just be like the constant functions over vertices. So it would be the all1 function and the all0 function. Okay, so I guess B0 is nothing very interesting, but I want to know these are the indicator sets of like the null empty set and also the entire V. So they are non-proper subsets of V. So this is something to note.
This is what we excluded in the definition of it.
Yeah, exactly. Proper, not proper subsets of V. Okay, and next we talk about, we want to figure out what is actually the cocycle of D0. Anyone have a guess what this is? Like what kind of functions would map to all 0 function when we apply this coboundary map on the vertices? So if we think about it, an edge will only be able to get 0 if two sides of its vertices have the same sign, have the same assignment. So that is to say, as far as you're connected, your components connected, basically all your vertex need to have the same assignment. So in some sense that is to say that Z is the span of all vectors, which are indicator of connected components. Indicator of one single connected component. So this is what Z0 is. And right, so if we consider now how to rewrite the edge expansion in terms of like V0 and Z0, we can actually do it. And it is as the follows. So as Avi noted, instead of taking minimum over like S, we can take minimum over functions in C0, so indicator of subsets, but we exclude this coboundary B0. And then what we get is, so on the numerator, we have actually the cut size. So what would the cut size be actually in in terms of all these notation we have, I claim that it will be equal to delta 0 of f. Okay, I probably should explain what norm is, but delta 0 f, if we think about it, like it basically is giving us the cut, because cut are exactly those edges that have different assignments to the two endpoints. Okay, so but the norm is defined to be basically a probability over edge such that delta f at this edge is equal to 1. So the norm is really just a probability. I'm kind of hiding what's actual distribution here, because for this talk, we actually don't really explicitly need a distribution. But in general, this distribution is given when you're given a simplicial complex. It's something induced by the structure of the simplicial complex. And every definition of this kind of norm are basically defined with respect to a consistent distribution over all level of faces. So, yeah. And
the distribution that's induced by the top level, by
yeah.
uniform on the top level.
Yeah, okay, yeah, that's right. Okay, then maybe I should say that. Yeah, exactly. So the distribution is basically the uniform distribution over the top level top level D faces. And it induces a containment relation to any layer in the middle, and also induces a margin distribution over all these faces in the middle. Okay, so the denominator is over there, we say it's the min of S and S complement. So I claim that it could be written as the distance from F to B0. So B0 in our case only have two vectors, all 0 and all 1. And the F would be the indicator of some set S. So its distance to 0 would just be the size of S, and its distance to 1 would just be the size of S complement. And we take the min of them. So actually, this notation is really defined by, we take the minimum over all G inside B0, and we take the norm of F minus G, where the norm is defined the same way as here, just the probability that the two doesn't agree with each other. Okay, so we see that this is exactly like edge expansion. So we have edge expansion if this is strictly greater than some constant eta. Okay, so this is the definition of edge expansion under these set of notations. And now we're going to generalize it to general d-dimensional simplicial complexes. So, and we'll give it a different name. So definition. So this is due to Meshulam, Walnut, and Gromu. I think we all studied this thing for different reasons at different points. Okay, so the definition goes as the following: like a simplicial complex chi is a, let's say, k-dimensional eta coboundary expander. The following holds. So basically, we replace the 0 by k everywhere. So for every function, basically for every k cochain that is not a cocycle, coboundary, that is not a coboundary, its image under coboundary map over its distance from BK, from the coboundary, is at least eta. So this is the definition. And we see like this exactly means like normal expander graphs are 0-dimensional coboundary expanders. Okay. Oh, and one thing I should note is that the minimum requirement for you to have a non-trivial number here. Like by non-trivial, I mean even a number maybe depending on the number of vertices that you have in the graph. The minimum requirement is that like bk is not equal to zk. So we've seen that bk is definitely contained in zk, but we also, sorry, this is wrong. Okay, the minimum requirement is that they have to be equal. So the reason being that if they're not equal, then we can just pick f from zk but not in bk and plug it in here. The numerator would be 0 because it's a cocycle, and the denominator would be something. So you couldn't get something like that's greater than 0 here. Yeah.
They're being connected here. I mean,
Yeah.
B0 is equal to Z0, even only if it's a connected graph.
Yeah, so yeah, you have non-trivial expansion, graph expansion if it's a connected graph.
Equality is like the weakest form of expansion. And
Yeah.
then becomes
Yeah, exactly.
better.
Yeah.
People who actually know topology think of this as like higher level connectivity.
Yeah, it is.
Yeah, actually, I want to give some intuition in the case of k equal to 1, like just going one dimension above, that's already something. So
But it's a good point that all these definitions come from topology. It's called, I don't know, homology theory, but it's specialized.
yeah, actually I want to comment on that in like the case of k equal to 1. Yeah, there's some actually very strong connection. And later we'll see motivation of studying these, and some of them are also like topological or geometrical motivations. So, right. Okay, so in the case of k equal to 1, okay, so first thing is, what is B1? B1, well, they're all the image of those indicator sets, so we know that these are just all indicator functions of the cut. Okay, and what is Z1? I guess I keep wanting to have a very intuitive explanation with what these are, but I don't know. I kind of don't have anything better than just saying they're indicator edges that intersect with every triangle, even number of times, which is essentially its definition. Okay, but there's something interesting to be said.
It's a labeling of the edges so that every triangle has either 0, 1, or 2 1s.
0 1s or 2 1s, right? Yeah.
It's kind of like a cycle. If you look at triangulation of a
Yeah.
surface, that you're going along triangles,
Yeah.
coming back to where you started, it's like it'll be even on each triangle.
Yeah, kind of a special cycle. You have to go like cover everything on the boundary twice, something like that. Yeah.
So like along triangles until you come back.
Okay, yeah. Right. So yeah, actually that's very consistent with what I'm going to say next, which is when is it the case that B1 is not equal to Z1? So it's strictly contained in Z1. So these are the things we're kind of ruling out. These are the bad things like having disconnected components in the graph case. So what are these cases? I claim that this case only happens if we have so-called one-dimensional holes in this simplicial complex chi. So what does one-dimensional holes mean? So what is a hole? Like just very intuitively, a one-dimensional hole is essentially just a loop like this. So the first requirement is actually it's a loop, which means that it doesn't have a boundary. It doesn't have a lower dimensional boundary, because a pass, for example, if I consider a one-dimensional object, a pass, its boundary are basically these two endpoints in one lower dimension, right? But a loop will be one that actually doesn't have this kind of one lower dimensional boundary, if that makes any sense. Okay, so no boundary. So a one-dimensional hole, okay, I think I should be a bit more formal here. one-dimensional hole. First, I claim this is, I want it to be a function f inside, at least exists inside C1. So it's a function over edges. So it's a subset of edges. And we say that it's actually a hole if first it doesn't have a lower dimensional boundary. So first if delta 0 f is the all zero function. So what is delta 0? This is basically delta 0 star. This is basically, okay, we just transpose the matrix delta 0, which means that delta 0 f is a function over the vertices. And if we write out fairly clearly, it's saying like, basically, we consider all the edges adjacent to this vertex, and edges need to be inside this simplicial complex, and f of b. Yeah. So in some sense, this is basically okay. If I have a path, if my f basically indicate a path, what happens is that the boundary of f. Yeah, this is actually called the boundary map. So maybe I should have said this earlier because this gives some intuition. So the boundary map applied to this function will actually end up giving me a function over vertices that are just non-zero in the start and end point of this path. Okay, so and because of that, this is saying like a path have boundary like these. So we want, when we say how we want something first, it's a loop, so it doesn't have a boundary. Therefore, we take this requirement, and that roughly means like it looks like some sort of cycle here. And the second thing of having a hole is it is itself not the boundary of anything. So, I mean, not a boundary. So F cannot be a boundary of anything else. Not a boundary of any higher dimensional object. So not a boundary of a bunch of triangles, basically that is to say. So this translates to essentially F is not equal to delta 1 star H for any H that's actually indicator set of triangles. So this would be what a loop is. So I guess more geometrically or more visually, that is to say, maybe one example of a graph with a hole would be like the donut graph, right? So
you can also define this using the delta. You don't have to use the delta stars, right? You can just.
Yeah, that's right. I guess that's true, actually. Yeah, I mean, homology are the same as cohomology. Yeah, I thought it was a bit easier to visualize, but I'm not sure. Yeah, maybe I should think about maybe doing that next time.
It's a theorem that this is the same.
Yeah. They have the same dimension. So, right. Okay, so I'm thinking about an example in which a simplicial complex actually have a hole is the following. So this is just my simplicial complex, and it consists of all triangles in this graph, basically. And I identify these two sets, and I identify these two sets. So you can imagine it's like, first you get a cylinder, and then you get a donut. Yeah, and well, just regardless how we triangulate this like surface, what's going on is that we know there is a hole geometrically in the middle, right? So it translates to a hole in this simplicial complex, which is the following one. Oh, well, there are many, but.
There are other colors if you want.
Oh, is this not very clear? Okay, I see. So I claim that this is a hole. So it's a hole. Okay, this point is the same as this point, so they're actually close together, right? So this is a hole because first it's a loop. I mean, because these are connected, and second, it is not a cut. in some sense, because it's not a cut, it's actually not a boundary of any set of triangles, right? Because even if I cut along this thing, I didn't disconnect the entire donut. It's still connected, right? It just become something like this.
But it still identifies two sides.
Yeah, that's true. Oh, you're right. So it becomes some sort of like cylinder. Yeah, that's right. So, but that is to say this is not a boundary of anything, and because of that, this is a witness of the fact that Z1 is not equal to B1. And in general, this is the case that if Z1 is not equal to B1, then there exists such a hole in this simplicial complex. Right. Okay, so next, I think I want to say a couple things about known constructions, but I really won't talk about any very specific ones until maybe the later half of this talk. So
Just to say, so this is what you said there about the triviality of eta. It's standard in topology to say that when this is zero, the k-dimensional there is no k-dimensional connectivity.
oh,
Right.
right.
And so in non-zero, we just want to do the analog of what happened in graphs, rather than talk about connectivity. We want strong connectivity. So we want the quantities to be big. So it's just so far formally it's a generalization.
Yeah, right. This is formally a generalization of the case in 0 dimension, basically. And yeah, for higher dimension, okay, maybe I should say this, like for beyond 1 dimension, I mean, this kind of thing still hold. Like if there is a 2-dimensional hold, then that means like B2 is not equal to Z2. Because as you pretty much see, this is coming from the definition. Right. Okay, so I will say a couple things about construction. So we'll later prove that complete complex or d-dimensional complete complex are one co-boundary experiment. Co-boundary experiment. And also there is the random simplicial complex model by Liu. Wait, actually, do everyone know what complete complex is? Maybe I should say that they're just all like a d-dimensional complete complex is just the simplicial complex induced by all sets of size d+1 hyperedges. Okay, so the linear Moshulem complex, basically what they do is, if they're considering a d-dimensional simplicial complex, they subsample the top level faces, and they actually, yeah. So
don't they demand that
yeah.
-1 level is complete, so it doesn't
Yeah.
satisfy your original.
Yeah, so you're right. They don't have this uniformity. I guess everything still makes sense. I mean, every definition still makes sense if it's like not really a uniform simplicial complex. I think I was just thinking about the examples I'm going to work with. They are all like have this uniformity condition. So yeah, maybe I should say like in general, it's not really required to define all these coboundary expansion and cosystolic expansion. Okay, like cosystolic expansion to come without this uniformity condition. Okay, so this linear Moshulem complex are also like, but they're also very dense, meaning like there are the number of edges adjacent to a vertex depends on n, basically on the total number of vertices in this graph. So it's not bounded. It's not bounded by a constant or anything. Okay.
But they also show that it's a constant.
Yeah, it's a. Yeah, I actually don't really know the.
So
let's say
I don't think that linear Moshulem actually showed this.
They showed it for two-dimensional complexes.
I think that what they do is that they showed, I mean, they wanted to prove like K connectivity, which is this like high-level connectivity, and for that they actually proved coboundary expansion of the complete complex. And I think that all that they do is sort of derive from that K connectivity. I'm not sure if they actually proved any like concrete bound on the specified
complex, no?
But
or maybe they look just at the threshold. They do
I
like
think that they only look at the
learning.
threshold of the connection, but
They do the threshold of that.
but it is known. I mean,
Yeah, probably
don't remember
by someone else. Yeah, now
who
I
has done this, but it is.
think. Yeah, name start with an M. Sorry. Yeah. So yeah, basically, I think they show like cohomology vanishes. So they show like a Z is equal to B, but I guess the number is shown later. Yeah, but these are omega 1 coboundaries. So in the special case of dimension d equal to 1, we actually know bounded degree coboundary expanders. So these are the LSV Rum-Nugent complexes. But for like a general large constant dimension, we actually do not yet know bounded degree coboundary expanders. So all the cases we know are like very dense ones. And I think another very important class I should mention are spherical buildings.
Let's be Lubotsky, Samuel, Vishnu.
Yeah, Lubotsky, Samuel, Vishnu. For those who don't know, these are graphs. These are simple complexes where like the vertices are essentially proper subspace of some linear space, and edges between them are also induced by containment relationship. And but a higher dimensional face is induced over a set of subspaces if you can order them in a whole containment chain. So this is the type of simplicial complex, and they're also dense, as you could see from this definition. Like, yeah.
And they're also coboundary.
Yeah, they're also coboundary. Yeah. So here, actually, I'm listing constructions of coboundary expansion. Yeah. I don't. So these are coboundary expander and coboundary expansion. So next, I want to just briefly talk about cosystolic expansion.
But before this, can you do an interpretation of this formula for two-dimensional complex?
Two-dimensional complex.
Yeah, you did it for one and we got expanded. Yeah, you did it, but what does it say? So it should say something. So, okay, you did when Z equals B or not, right? So that's one-dimensional whole. But when is it big? So what do we need to be big though? Exactly in this quantity.
I see.
We want to say that if the denominator is big, then the numerator is big, right?
Right.
So
okay.
can we, in terms of 0-1 labelings of the edges of the graph, what does it say about the triangles and the cuts?
Okay, I see. Think for a moment. So I guess it's saying that if you're far from a cut, then you have to, it will be observed by many triangle parity checks.
So triangle parity checks means that there will be many odd triangles.
Yeah, there will be many odd triangles in delta K of F, delta 1 of F actually.
So maybe it's a good point to say that if you are a cut, then every triangle has an even.
Right. Okay. Yeah. Okay. That's
right.
That's good. Right. Yeah. That's right. If you're a cut, then every triangle intersect a cut with even number of times. I guess we can think because for every triangle, I mean, there are only so many
All the
assignments.
cuts, maybe, I don't know what, yeah, okay.
Okay, it depends. I mean, if they're all on the same side, like if all the vertices get the same assignment, we of course have like there's zero intersection. If they don't get the same assignment, I mean, the only thing that can happen is really one is on one side and two on another side. And in this case, let's say 1, 0, 0. So the cut would be, so it would be a intersected triangle even number of times this cut. So right. So if you're a cut, basically, like if you evaluate the function overall along all triangles, it's just always 0. Yeah, and the point is that if your function is far from being a cut, then that should be witnessed by many like small triangles of weight proportional to the distance from the cut. So that is what that statement is saying.
It's a bit like locally the stability of the
Yeah.
space of cuts. It's like during the cut is 0, and if you're far from it, you can pick a random triangle. You'll prove that it's not a cut with probability proportional to how far you are from the.
Yeah.
That's the Kaufman, Lubotsky-Kaufman.
Yeah, that's a Kaufman.
It's like a probability testing, yeah, or local testability of course.
Right. Okay, nice. Okay, I'm actually going to talk about it as one of the motivation, but probably it's already clear. Okay, so
What for the spherical buildings, for which homological dimensions are they expanded? Is this still 1 or is this for other degrees too?
also for other degrees, yeah.
And is this only for split groups?
I actually don't know what that means. I'm thinking about like just over finite fields, but
Yeah, but I mean spherical buildings, they encode the parabolic subgroups of a group. And if it is a classical group, it's different than if the group is not classical, but okay.
But over characteristics, do we are talking about other what characteristics? She's talking only about characteristics too.
But the building will not be
But the
for a group in
spherical building-
You
characteristic.
can talk about
The
group
spherical
coefficients,
building-
which is F2 here, but like the spherical building, like you can take various groups and define spherical buildings using these groups, and you can play both with the coefficients which are here F2 and like the group that you're using for the spherical building. So
And this can be over another field.
yes,
yeah.
and they don't even have to be classical.
Yeah, and not split, so it can
on.
be forms of.
Yes, but they're all known to be Coboundary expanders
over F2.
over F2, and I think that probably the proof should carry for
Finite
other,
groups.
coefficients as well, because it's like a very geometrical proof.
So, right, so yeah, and actually to get higher dimensional coboundary expanders, we actually have to increase the underlying field size when we're constructing this spherical building. So yeah, so they're not necessarily over a vector space over F2. Okay, so we're actually I take back what I said. I think that has more to do with the dimension of the vector field. So yeah, it's but in general, I think the lesson is still like we can have other finite fields. Okay, so I'm going to briefly talk about cosystolic expansion. So it could be viewed as just a relaxation of coboundary expansion. Definition. So
Just to understand from this list, it's an open problem to prove for the coboundary expansion for sparse complexes in dimension 2 and higher.
yes, yeah, that's right. Yeah, it's an open problem to find. Well, okay, maybe to show coboundary expansion for first to show coboundary expansion, maybe for some existing construction of like other types of more relaxed notion of high dimensional expander.
Even existential results are not
Yeah, bounded degree, yeah,
bounded degree. Yeah.
right.
So the random construction doesn't give you that?
The pseudo-random construction.
No, the random.
Oh, the random, they give, but they are not like a bounded degree. They're still a very high degree. So the here bounded degree really means like I want every vertex to be in bounded number of like d-dimensional faces. So yeah, so this one I think still you need like to be in polynomially many. Well, at least polylog many like polylog in many top level faces. So that is a problem.
And so this also, I guess, you mentioned that they are unrelated. So in the zero-dimensional case in graph, we have the trivial inequality. So we know that this edge expansion is up to polynomial is the same as the eigenvalue part.
Right.
Whereas we don't know this for higher dimensions.
Yeah.
We know it's not true.
I think we know it's not true. There, at least, like if one is a really okay, I should say this. There are examples of very good Coboundary expander that are actually not generalization of that are not a good high dimensional spectral expander. For example, those kind of results are no. I guess I'm not sure.
But I thought it was the opposite way. We know how to construct spectral expanders which are sparse in any dimension.
I see. Yeah.
And we don't know this for Coboundary expander.
We don't, right? So
that's a weaker definition in a sense.
We know it's not true. You can construct a very good high dimensional spectral expander, which is not.
Yeah. Okay.
Right. I think actually Yotam even taught me one of those examples, which is a tree, right? Like actually if you if you take a tree, well, okay, locally tree-like expander, and you add like triangles by connecting all like vertices that are distance 2 away from each other. So these like basically form a clique among all its neighbors and add all the triangles appear in this clique. This actually will give you non-trivial local spectral expansion. But because of a reason we'll later see, this actually cannot be a Coboundary expander because you can draw it on the plane pretty nicely, I would say, in some way. Yeah. Okay, so yeah, that was. Okay, so a d-dimensional cosystolic. Okay, maybe I should say I has theta mu cosystolic expansion in dimension k. So the relaxation we're going to make is that we don't have to require bk to be exactly equal to zk. So to compensate for this relaxation, instead of considering f that's coming from like c1 exclude b1, we actually also exclude everything in the kernel. And we just require that, okay, the rest of the things are still similar to before. So, okay, instead of I should do k. Okay, delta k of f over the distance from f to zk. Is greater or equal to theta. So this is the first requirement. So this is just replacing bk with zk here. And for all function that is inside zk, but not a coboundary, we require that f has weight at least, Hamming weight at least. So like, I guess translate to maybe zero-dimensional cases, this is saying like you can have disconnected components, but all of them need to be large. So this is the relaxation.
And what is this in dimension 1?
I guess in dimension 1 is you could have holes, but they have to be big. Great.
So
Actually, wait, maybe that, sorry.
in dimension zero, you said all the connected components have to be large, but what about the other one? What is this?
The other one is saying like the coboundary expansion is saying that you can only have one connected component.
No, this,
Oh.
what's written here? Systolic expansion in
But
dimension
that's
zero.
the code decay instead of big.
Oh, it was just in terms of the graph, does it mean that each connected component is an expander?
Oh, I see. In terms of a graph, yes, I mean, in zero dimension, yeah, it is saying that. Yeah. Okay, but the question about what does it mean in one dimension? Okay, the first condition. Actually, that's a good
So
question.
you're looking only at labeling which have ones on a constant fraction of the edges.
Yeah.
And what does it mean being in the kernel?
In the kernel means it's a loop.
The loops have to be really long.
Yeah,
This is the systole, right? It's like the short.
I was going to say that, but I feel like that's the opposite. And I think cohomology and homology actually translate to each other. The lengths of cosystole and systole, I'm not exactly sure if they translate to each other.
What's on the right says that if you have something in ZK that's not in BK, it's like something in a donut, something that goes through the hole.
Yeah.
Along triangles and wraps, and it cannot be very small. It had to be a fat donut. So we're getting close to that.
The donut is given.
But it cannot be a thin donut. It has to be a thick. You have to go around it. You have to travel a long way.
It can be a thin donut, but you are looking only at thick.
It's just a condition on the right.
The second condition would not allow it.
The length to go around the hole has to be a constant fraction.
Yeah. Yeah, and this one.
This one I don't.
Yeah, you have to say I don't have a good idea of what that means even in one dimension.
The thing about going around the hole, these are like you're talking about the hole, but the hole is not it's like a boundary, not a coboundary. The fact that the dimensions are equal, so I'm not sure if you also get like this robustness.
CK is the kernel.
Right.
It's everything with even numbers of triangles, right?
Right.
So that includes cuts, but also includes things that go around, like paths that go around, let's say, the hole that are not a cut.
So
Okay.
Right, so that would be something in ZK that's not in BK.
I think at least in the
Right, but you're giving an example. I mean, it's not directing the.
In
I'm not
particular,
sure
right,
if
but this condition implies in particular that to go around the hole, it needs to be a long path.
I think
But in the torus.
Yeah.
This is not.
In that example. No, I'm not characterizing it, I'm saying it's an example.
yeah, I also don't have I don't have a good geometric intuition of what this really means. Great. So maybe if we're talking about the motivation of studying these two notions, maybe I want to say we know much more about constructions of bounded degree cosystolic expander. So so first, the Lubotsky, Samuel, Vishnoi, Ramanujan complex. These are a family of bounded degree d-dimensional cosystolic expander for any constant d. So we do have that. Yeah, we also know like the Kaufman-Oppenheim construction, the KO construction. Well, maybe I should call it complexes. From like coset geometry, they are also a family of bounded degree cosystolic expander. Yeah, so okay, anything else I want to
So
say?
any good way to see why, why this is so much easier than that. Why consistoric is,
yeah, okay.
meaningfully simpler so that it allows these guys to be consistoric and not co-bounded.
That's a good question. Well, I have some answer that's probably not the most intuitive answer. That's coming from like how people are proving cosystolic
Yeah,
expander.
so that's probably the same question.
Yeah, why do people have to prove that way?
But because,
Yeah.
first of all, is there a connection of consistoric to spectral or no?
No.
So the same comes as example you mentioned, all this consistoric. Something that's spectral,
I think, I mean, at least part of the answer is that co-boundary expansion, as like Siqi depicted, it connects to something that's very global in nature. Like you can, sometimes you can't understand whether you have a hole or not unless you're actually looking at the whole complex. Whereas it turns out that like you can prove consistoric expansion using very local methods, like looking only at neighborhoods. You can sort of infer something about like this quotient or the size of the boundaries, and so like I mean it's not like by no means this is not easy. Like Brian Kaufman, they had like a whole lot of work to show that you know these LSV complexes are consistoric expanders. But like all the methods we know to show like consistoric expansion is like local methods. So this is why this is like a relatively easier question.
So you can understand this quotient in somehow local terms.
Yeah.
Is it? But I feel it's not equivalent. It's more like there are local conditions that imply this. So, and people actually would show that maybe potentially stronger, I mean, actually is stronger notion, and that implies this. But for this specific ones, I mean, it does still look pretty global to me though.
It's a minimum on a smaller set. You get more information that you're far from Z, not from B.
Of course, yeah, but it doesn't help me anyway, but because I don't see any, I don't visualize any of these objects. I have another question on this higher level question. Are there known applications of consistoric or co-boundary expanders that are not applications of spectral?
Yeah.
Yes, yeah. Okay.
Yeah, there are, and I'm actually going to talk about, I guess, two of them in the motivation part. Yeah, maybe I postponed motivation part a bit too far. Okay, so now.
You promised to give it, so it's okay.
Okay, good. So I want to give like I wouldn't necessarily say 3 applications of co-boundary cosystolic expansion, because some of them, I mean, it's not like the best type of object that can be constructed using all methods, but among all methods, but I would say like still 3 different connections, 3 connections to 3 different things. That maybe help you to see why they are interesting objects to study. So, like, the first one I want to say is about locally testable codes, but I think I guess Zev already figured that out, but I will just still have it here. Motivation number 1, like locally testable code.
When I said wasn't that's not how they construct the locally testable code. That's just those codes have no distance, so they're
right. Yeah,
it's a different. Anyway, it's not what I.
Oh, in no worries. I'm actually going to talk about that code that doesn't have distance. But I want to say like. Yeah, like probably people have heard about like high dimensional expanders have to do with the recent C-cube locally testable codes, which have constant relative distance, constant rate, and also constant query, like arity in the query. But That one, yeah, that one does not directly come from any of these coboundary or cosystolic expander. I think that one actually, yeah, it has more to do with spectral expansion, if I'm to say. To my degree of understanding of the proofs, I feel it has more things to do with like local spectral expansion. But I wanted just to say at even the syntax level, this coboundary and cosystolic expansion have so much similarity with locally testable codes, which is the following. So locally testable codes, we say that a code C inside Fn is, let's say Q, comma, eta, LTC. If there exists a parity check matrix, that is low density. So a parity check matrix would be in it will be a matrix in m by n matrix, and such that each row has weight bounded by Q. So each row have only at most Q non-zero elements, so it's a very sparse check. And of course, there's an additional requirement you need to satisfy about the testability part, which is that such that if we look at this quantity, we consider all words that's not actually not words, all vectors that's actually not really inside this code, so are in F. Exclude C. Then we have that if we apply the parity check matrix to it, this vector's Hamming weight is proportional to the distance from W to this code word space. This we require to be at least eta. So syntactically, we can see this is already pretty close to like coboundary and cosystolic expander. So if chi is k-dimensional coboundary expander, then like we can set this C to be equal to bk, right? And then we will get a k plus 2 comma eta. Okay, if eta is the coboundary expansion parameter, locally testable. Yeah, here I didn't say anything about distance, or because this, as I was pointing out, this code have terrible distance because, you know, especially if you're a sparse coboundary expander, it has terrible distance because you can just change very few, bits in the code word by just flipping one message bit, and that just says that distance is terrible. Okay, so this is the coboundary expansion, and okay, if it's a
in this case, H would be delta K.
Oh, right, yeah, that's a good point. So H would just be equal to the matrix delta K. Okay, if instead we have cosystolic expander, then we can set C to be equal to ZK. And then H would still be this.
But then you are testing only.
Yeah, I'm testing, I'm testing basically all the things that's outside the ZK. So, yeah, so those are not code words. Yeah, and they will still be the same parameters.
Yeah, and all these words will actually be constant fraction. We have a constant fraction of 1.
Yeah. Oh, I see. Yes. But that's just a requirement for things that are like, for things in ZK, but not in BK.
Oh,
For things in BK, it would still have really low weight because we can imagine it comes from just indicator of one K minus one phase. And then it would really be just a tiny fraction of the weight. Yeah. So yeah, in general,
the
these
things you are testing only things that are not in ZK.
right.
The condition in Cosystolic applies only to the denominator talks about the distance from F to ZK.
Yeah.
So what you are testing are only words that are wrong.
Yeah. Only words that are actually doesn't pass this H test or this delta K test. Right.
You're not testing anything in BK.
No, I'm not testing anything in BK in the Cosystolic case. Yeah. Right.
I mean, in ZK minus BK. Yeah, you are not. Yeah.
Okay, I think that what Siqi meant is that if C is equal to ZK, you still have very light code here, so you still don't get distance. The second requirement from Cosystolic expansion says that you have distance if you are in the code and you're not a coboundary. So this is sort of.
And you are testing only these words.
No, you're testing.
You are testing. Oh,
Yeah, we're testing.
okay.
Oh,
It
okay.
doesn't have to be
Okay.
anywhere. Like if it's in ZK, it will just always pass the test.
Okay.
But you don't actually get distance, but you get something that's like as close as possible to distance that you can. Because like a coboundary can always be very light if it came from a very small set of vertices. And this is sort of saying this is the only example that you get.
Yeah, that's good. Yeah, maybe it wasn't quite clear. Okay, so the C is actually we're thinking about this linear code, and C is the entire space of ZK. And yeah, we actually didn't use the second condition on a mu eta Cosystolic expander. Like this mu part, we didn't really use that. So actually, a slightly weaker thing could also imply this. Yeah, and both of them are codes with terrible distance. Okay, so this is the first connection I want to give, and the second one. Is about the notion of topological overlapping. Oh, and I should say the first one. Okay, the first is due to Kaufman and Lubotsky. Kaufman-Lubotsky. Okay. The second motivation is, or connection, is with topological overlap property. This is studied by Gromo. And later there's simplified proof by Doctrick. Kaufman. Webster. So what is topological overlap? Basically, we say this is actually not a property of simplicial complex, but like actually like a polygon complex, which kind of means like instead of just thinking about things as hyperedges, we actually think about them as like actual like we also include points, for example, on the edges, and also points if I have a face. I mean, this is I'm considering like this entire thing as a face, but not as like a discrete set of points. So see, okay, I should say a polygon complex has C topological overlap in dimension. Okay, means that for all map F that maps this complex to Rk. So this map basically need to be continuous. So I mean, one way we can think is this map is just first we map all the vertices to points in the space, and then we map all the edges to continuous path in the space, and higher dimensional face to like surfaces in the space. So this is the map, and it has topological overlap property. If for every kind of embedding into Rk, we have that there exists some point in Rk that intersect with many of the K faces, such that if we take the probability over K faces, the image of the K face in Rk contains B with at least probability C. So this is the topological overlap property. And I think in zero dimension, it's not too hard to see that actually Coboundary expansion gives you like this this kind of thing. So okay, let me say for dimension, consider dimension k equal to 1. Then actually zero dimensional Coboundary expansion gives you one dimensional topological overlap, because this is equivalent to like we just embed the set of vertices on the real line and look at the set of edges. So for any embedding, what I can do is I can pick a point such that there's half of the vertices lie on its left and half the vertices lie on its right. S and S complement. So if I do this, then what ends up happening is the probability, the number of basically the number of edges that P lies in is exactly the size of the cut across S and S complement. So because we have Coboundary expansion, we know it's at least eta times cardinality of half of them. So well, we pick it to be half, so it's eta times 1/2. So dimension 1 is easy. I guess I want to go one higher dimension, but maybe give some intuition. But I think it's yeah, we'll see. We'll see if it makes any sense. Okay. So in general, for dimension 2, I want to say that zero dimensional and the one dimensional Coboundary expansion would imply two-dimensional topological overlap. So here we make some simplification. We actually, instead of considering all embeddings that basically are continuous, we actually think about maybe just all affine embeddings, which means like all the edges are mapped to straight line segments, all the faces mapped to live in some like hyperplane. So they're just much simpler to deal with. So so in such a graph, in such a simplicial complex, any embedding is equivalent to, okay, I just have a bunch of vertices, and once I fix the location of my vertices, I mean, it kind of determines already everything about this embedding, because all the other things are just derived deterministically from the position of the vertices in these affine maps. I don't know, I'm just drawing random things. So, okay. So one thing to note here, like I just wanted to give some intuition. Why is this related to coboundary
So
expansion?
just to complete this picture, what you want is a point in the plane
Yeah.
that exists in a constant fraction of the triangles of the
Yes.
of the compass.
Right, okay, yeah, right, so, yes, so we want to find a point that exists, that basically lives in constant fraction of the triangles. Let's say I pick some point P, like, so I claim that basically the number of triangles that P is in can be written as this, okay. Is equal to the norm of one function. What function is it? So I'm thinking about emitting a ray of light from P to infinity, like just any direction is fine. Let's say this direction, and call this line segment L. Well, not really a segment. Call this L, and then I define the number of triangles P is in by applying the delta 1 function to the following set of edges. It's a set of edges that actually intersect L. L. So y is, okay, maybe instead of saying number of triangles, I should say fraction of triangles. So why is this the case? So imagine like, if I have a triangle and P lives in it, so no matter which direction I draw this line L from, it will intersect with exactly one of its boundary edge. And because of that, when I consider the function where I give this label 1, this 0, and this 0, I will have that when I apply this coboundary map, I get a 1 for this triangle. So on the other hand, you know, if a triangle does not contain P, either this line, this L just doesn't touch the triangle at all, or it touches it twice. Okay, let's exclude the very weird case when it just touches one of its edges. But in general position, it will be something like this. So then we can define the function to be 1 on these two edges and 0 on this edge. And then like if we apply the coboundary map, this triangle will give us a 0. So this is exactly how you count the number of triangles. So it's by constructing functions like this. So this is good because we can now use one-dimensional coboundary expansion. We know that this is greater or equal to some eta times the distance from this intersection with L function to B1. So we know B1 are just a set of all cuts, and this may not be cuts. In some sense, this is almost half a cut. Well, okay, just a partial cut. So it could be that, okay, if this quantity is large, then we're already done. If this is like omega of 1, we're already done, because that is to say like this P actually lives in constant fraction of triangles. The bad case is when this P actually doesn't like all P and all L doesn't give me something that's omega 1. That's a bad case. And we're going to try. The intuition is that in that case, one should try to derive a contradiction saying that if that's the case, it implies that we don't have zero-dimensional coboundary expansion. I don't think I can really do the proof here, but I think some intuition might lie in the following example. Like, let's go back to the very, very common picture that I keep drawing today. So let's think about having, actually not even 2 layers, just having a stripe, a very long stripe. And I triangulate the stripe. Actually, I think I do need a second layer, but okay. So in this example, actually, it will be one of the example that of some complex that have one-dimensional coboundary expansion, actually constant one-dimensional coboundary expansion, and but have some embedding such that all P will have give a very small like distance away from coboundary. The reason is, I mean, no matter what kind of cut I give, I mean, even if I have a super large partial cut, what could happen is that I can just direct the rest of the cut by adding this part. So this part really intersect very few edges, which gives and complete this entire ray into a cut. So this basically says that this quantity is like a little one, very small. But we can see that I would claim that this is intuition of what kind of graph you would get if you have like one-dimensional coboundary expansion, but no good partial cuts like this. And because this is such a long stripe, we know that it doesn't really have zero-dimensional coboundary expansion because it's a poor edge expander.
So is it that if you have such a line, you would simply map all the you project the vertices to that line, and this will give the counter example to the zero-dimensional expander. That's how you get there.
No, actually the proof actually doesn't go this way. Yeah, the proof involves actually consider the space that this embedding lives in and triangulate it. And actually from there, they define some like a homotopy cochain, homotopy between chain complexes and work from there. But similarly, I think they're aiming for deriving contradiction. And I don't think I have a good enough understanding of that proof to say like if actually it's following the exact same logic.
Even in the affine case.
Even in the affine case, yeah, I'm not sure if that's the logic underlying it. Yeah. Okay, so okay, the last motivation.
So about this motivation,
Yeah.
is there a reverse connection? If you have a topological overlap or affine overlap, do you get cosystolic or coboundary or something?
Good question. Thinking, is there embedding such that every cut can be, like, sorry, every function f can be written?
I think that in dimension 1, you can be a very good topological overlapper if you just take an expander graph and connect it with one edge to some like small complete component. Now like, because
Again, you take an expander.
take a very good expander, which is has topological overlap in one dimension.
Connect.
Now you create like a sparse cut by like say adding like another component, maybe, and connecting it by one edge. Like even think about like two complete complexes connected by one edge. Still, you get like a constant topological overlap because you still have like half the graph is an expander. So if you want to say that topological,
Well, we are talking about triangles.
I'm saying in dimension 1, you take two complete graphs,
Yeah.
connect them by one edge. This is a terrible edge expander. It's not a boundary expander, not a cycle expander, nothing. But if you project it to the line,
So even in dimension 0.
yeah.
Can't you even just make the example like disconnected and it's still?
Yeah, if you take it disconnected, then you could still have told me, oh, but maybe it's a cosystolic expander now or something. So I think that maybe you can say that, like, I mean, if you can say anything, it must be that, like, inside the graph, you can maybe find a large component that's a good coboundary or cocycle expander, but it has to, like, anything you should say has to deal with like these situations where you can just sort of perturb a little or
Yeah.
Yeah.
And for this other construction in every dimension,
Are there?
they come from the consistolity.
Yeah.
Yeah.
They actually come from Cosystolic. Yeah, they have construction.
So this construction solves the Golomov problem of sparse topological overflow. Okay.
Yeah, that's a result by Kaufman, Kasten, and Lubatsky. Yeah. Okay. So I have one more application. Which is of a very different flavor. Which is about like explicit hard instance for maximum KXOR. I think actually this one I couldn't really explain much of the intuition behind it because I think it requires too much things that's not covered here. But at least I can talk about what's the construction of these like constructions of these hard instances for maximum KXOR. This is actually an application for Cosystolic expansion, not Coboundary. Actually, you would need a ZK not equal to BK for this. And oh, I should say this is a result by Deneuer, Thomas, Harsha, and Tusian. Okay, so and there's follow-up work by Hopkins and okay, so the hardness is hardness for resolution proof system and also hardness for sum of square algorithms. Okay. For instances, if I'm given a k minus 2 dimension.
So maybe you just want to say what the problem is. I mean, you are given just a system of k-linear equations, 1, 2.
Yeah.
You want to say that it's hard to approximate the number of satisfied by the best design.
Yeah, right. Okay, yeah, that's right. So I basically KXOR means like I just have a bunch of random variables, and over these random variables, I have constraints of the form.
They are random variables, they are not. You are looking for the best assignment.
Yeah, yeah, random variables. But yeah, sure, best assignment.
The variables.
Yeah, they're that's right. Right, they're variables. Okay, so yeah, we have like a bunch of variables, and we also have a bunch of equations over these variables that we want them to satisfy, and each of them involve like k variables, and we want their XOR to be equal to some specific bits, 1 or 0. I guess just complete this. It's equal to some b. Okay, and the maximum KXOR is just to solve for the assignment over these variables that to maximize the number of equalities you satisfy. So this is the problem. And from a k minus 2 dimensional Cosystolic expander, so let's say with eta and mu, we could get allegedly get hard instances for maximum KXOR against some algorithms and proof systems. Okay, so how are these examples given? So basically, the set of variables is exactly chi of k minus 2.
Or maybe I say just one more thing. So people who didn't see this is an NP-hard problem, and in fact it's hard to approximate by the PCPCO. And so you are trying to find algorithms to find reasonable approximations. Then the resolution sum of squares describe families of algorithms to heuristics for this type of problem. And it's also known that random instances are
hard.
hard. For
Yeah.
this resolution, I think, I don't know if for some squared maybe, no. And you are looking for explicit hard instance.
Explicit hard. I think I made a off by one error. I think here I really should write K-1 dimensional cosystolic expander. So the random variables are Kx minus are like
Not random variables, they are variables.
I keep making this. Okay, so the set of variables are the K-2 faces, and the set of equations are given by delta K-2. So basically, they're induced by like K-1 faces, and you just look at all the variables inside that face, and yeah, and some assignment inside C K-1. So basically, the constraint would look like you want delta. Satisfying assignment would be a G inside K-2 such that delta K-2 G is equal to F. So this will be
This is the code you defined before.
yeah. This is
the system of equations is the test. You know, you just every line is a test that you can apply a parity check test, right?
This is not even a test. This is just a coboundary map itself. I think there's not yet any test here. So it is. Yeah, but okay. I think you're right. So I think you're right that okay, if you view the equations, the system equations are exactly the test we've seen in the previous locally testable codes. But yeah, they're all related to this coboundary map. Okay, and but maybe now it's start to be clear to see like an instance. For an instance, to define instance, one need to define like the set of equations. The set of equations that need to satisfy, and equations is given by like this delta K-2 and also some F in K-1. So this pair is the equation, and the hard instance is.
So F is B really, right? You could have written B for this. I mean,
Yeah.
It's like F.
Yeah, that's right. So if F is in BK-1, then instance satisfiable. Like, oh, okay, I guess satisfiable or yeah, it could be satisfied. Like all the equations could be satisfied. But if F is not inside it, then one cannot really satisfy all of them. And the hard instance here are actually exactly those ones where we pick F to be inside ZK-1 exclude BK-1. So for those in ZK-1 exclude BK-1, well, why is it hard? I mean, actually first for F that's outside ZK-1, it's actually easy. So first we know that it's not satisfiable. But the second thing we know is that also it's very easy to form a refutation for the fact that it's satisfiable. For instance, like because of all the loaded state parity checks, so one parity check can already witness that this is not fully satisfiable, for instance. So for any F that's not inside ZK-1, it's actually a simple case. And this
Sorry, what are we trying to do? Is this about certification of non-satisfiability or what? Are we trying to find an algorithm to approximate
this is
the
final
density,
refutation.
or we are trying to find a proof that it is far from satisfiable?
This is actually a proof that it's far from satisfiable. This is what we're trying to find. So it's
So
like
it
a
is proof
refutation.
complexity, not in the algorithmic side. Yeah.
Yeah.
No, resolution and sum of squares can be viewed as algorithms, and they can
I see.
also be viewed as proof systems.
I see. So,
You're talking about the proof system.
right, yeah, here I'm talking about the refutation hardness. So
It's a quantity hardness. It's hard to refute. It's hard to prove that it's far from satisfiable, I guess.
right,
Right?
yes, yes. So I guess yeah, I'm probably not going to explain much about why these are the hard instances, but yeah. So this is also due to the Cosystolic expansion that they're actually hard instances.
I think it's generally known in proof complexity as for weak systems. Weak, I don't know what you want to call weak. Resolution is certainly weak. Sum of squares, in some sense, is weak. That expansion of, that expansion is, the expansion of the instance when it means what you want it to be is a limitation for these proof systems. You can get exponential low bounds. In some, so I guess here what's needed was the kind of expansion needed is this high dimensional expansion. Yeah, it was known for random instances.
So in the rest of the time, I think after talking about these three motivations, I want to just talk about how to prove like coboundary expansion, like one of the most useful way of proving coboundary expansion, and we can go through together like how to prove at least like complete complex is a coboundary expander. I think even that is probably not immediately obvious. So so let's look at that. So realize we didn't take a break, and this is way too late to take a break. Sorry about that. I did. I went much slower than I imagined.
By default.
I mean, if you don't need a break, why would we?
When I'm sitting there, I usually would go to the restroom, but I don't know. I won't be offended if you guys choose to do that. Yeah. So okay, coboundary expansion.
So there's no, you gave a talk in CS about the random model for spectral expanders, right?
Yeah.
So for this coboundary, there's no analog kind of sampling. If you sample according to that distribution, for example.
Actually, I think we suspect that the model I talked about also would give coboundary. I mean, it definitely would if we go to a higher enough density.
But not constant degree.
Oh, constant. Oh, yeah. I think randomness is really bad in dealing with bounded degree because this kind of sampling, you already probably need polylog to be connected or anything. So
it's even for spectral.
Yeah.
There's no random model.
Yeah, I mean, yeah, coboundary also need to be connected. So it's like, I don't know of a constant degree, like a random model. I think, yeah. I mean, we don't even know like bounded degree general explicit construction. So this is I guess this is a strictly harder question. Yeah. So coboundary expansion for complete complex. So I will only just as an example deal with the case of like one-dimensional coboundary expansion, but at least the proof idea very nicely follows, like syntactically just go through if you replace one-dimensional with other dimension. So let's start with that. So I think the general idea is the following. Recall that coboundary expansion, what do we want? We want that for every f that's not in the boundary, coboundary, delta 1 of f over the distance from f to v1 is at least the eta.
So every labeling which is far from a cut has many odd triangles.
Oh yes, that's right. Yeah, far from a cut means you're also having many like odd intersection with triangles. That's right. So I guess in complete complex, okay, I guess the general idea is the following. Once we're given f, we want to define define a, well, okay, sometimes people call it decode. Want to find a G inside C0 such that, you know, F agrees with G as much as we can. So F agrees with delta 0 of G. Because this delta 0 of G, we'll use it as an approximation for this distance from F to B1. So
You're already going in the other direction. Let's say if F has few odd triangles, then there's a labeling of the vertices.
yeah, I think actually I will still go kind of the directions we're usually thinking about this, which is if F doesn't agree with G on this delta 0 G on some point, then actually I will see at least some triangles, some fractional triangles. So yeah, but the way of defining this G is called, we do it using the so-called the Coe method. The Coe method is pretty general paradigm, so usually it goes as follows. We find a base point V0. And okay, note that now I'm talking about dimension 1, so F is a function of edges. So now we set G V0 to 0. So honestly, it doesn't matter what the first point would go. And second, for every U that's not V0, what we do is we define a path from U to V0. So the Coe method would involve like defining this path, PU. It's a collection of edges that goes from U to 0. Okay, maybe I should do a better job. W is 1. Okay, so then after having this path, we can define G very nicely as GV0, GU is just equal to, with some like F over all edges on this path. F of G plus G of V0, but since this is 0, it doesn't matter. So
trying to be at least consistent
on the path. Exactly. So we're trying to be consistent on the path. So what that means is like, yeah. So how should I say this? Like if we consider like, okay, this is not what actually we'll do, but if we consider like all the partial path on this line, and we assign all these intermediate node also using this method, then what happens is that on this line, I mean, G will always agree with F on this path at every edge. But that's not what we're actually going to do. But that's just intuition.
This choice of path is clever or arbitrary?
It's clever. Yeah. The Coe method for dimension 1, besides defining P, we also define set of triangles UW for every UW that is an edge. What are these? These are a set of triangles such that whose boundary of T UW. So here, okay, sorry. So maybe I should write. If we apply the boundary operator, which is the inverse of the reverse direction of our coboundary thing, to the indicator of this set of triangles, we would get an indicator over a bunch of edges, and these edges are exactly UW plus a union this path, PU, union this path, PW. So it's probably good to draw a graph here. So far what I've been doing is I have this V0 and some pass towards U, another pass towards W. And right now I'm defining triangles with respect to this edge. And we define triangles so that the triangle's boundary are exactly this loop we see here. So it's kind of trying to, you know, fill this shape in the middle. Yeah, something like that. Right, okay. So, and the proposition that we'll be using is the following. Okay, so far I didn't say how to find them, but we'll see. For a complete complex, it's very easy to define how to find them. Like it's very easy to define a good set of triangles and passes. So for the proposition is the following. If F UW is not equal to delta 0 of GUW, for some UW that's not V0, right? And for this G also defined exactly in the way we see before, then.
So you define G for
a set of like, for V0 and path PU and triangle sets TU.
so you define it only for the, you didn't define it for it yet, but it's the same idea. You go along the triangle. Yeah, what? You define G for
vertices.
For vertices.
Yeah, G is a function over vertices, and we're comparing F with delta 0 of G. So this delta
is the function on vertices and you all G of UW.
Right, because I'm applying the coboundary map. So the coboundary map will map G.
Got it,
yeah, no worries. So, so the statement says that if the two of them doesn't agree, so then that means there exists some T inside this triangulation for the edge UV such that delta 1 of F at this T is equal to 1. I mean, we can kind of immediately see why this kind of proposition is nice for us, because this is kind of saying if we have some distance in the denominator, then we also have some gain in the numerator. So this will help us to get an upper bound if this is small. Right, so let's talk about the case of complete complex. Complete complex. So let's say in complete complex, very simply, I will just define PU. Okay, so I guess there are 3 steps.
Complete complex field means that we have n vertices and all triangles on it.
Yeah, so that's a good point. So you probably, as Avi was saying, like if we have this kind of statement, if we pick a particular V0, these only consider like triangles. Basically, this may not cover all triangles. That could be a problem, and this may not cover all edges. That could be a problem. We'll resolve that problem by sampling V0 randomly. Yeah. So the cone we consider is the following. So first, V0 are sampled randomly from I0, and once we have V0, we actually fix PU to just be the edge UV0 and the TUW to just be the triangle UWV0. So it's like very trivial over complete complex because every edge and every triangle are present. Okay, so what do we know from here? We know that, okay, let's write the denominator here. If we subtract from FB1, I claim that this is upper bounded by, if I take expectation over VV0, distance from F to delta 0G with subscript V0. So this GV0 is just the function defined via this cone, specifically with V0 specified. Okay, so I mean, this is the case just because I mean, this is the optimal, and anything inside this could be no smaller than optimal, right? Okay, and secondly, we want to rewrite this. So what is this? So basically f and v0 would agree already on many edges. Those are exactly the edges adjacent to v0, right? Because we kind of assigned g0 so that for every edge adjacent to v0, this would agree exactly with f. That's how it's defined. So I claim that then I can replace inside by probability UW that does not contain v0. F of UW is not equal to delta 0 G v0 UW. I mean, this is just a bit of Riemann normalization, and we actually make the probability a bit larger than before, when it should be. Now we can apply our proposition. So the very nice thing is that all our triangulation consists of exactly one triangle. So this could be written as expectation over v0, probability over, UW v0, such that delta 1 of UW v0 is equal to 1. Okay, so yeah, that basically becomes a numerator if we switch, if we consider the randomness from both things here. This is exactly equal to probability over a random triangle. And this is equal to. So we basically, this is just a coefficient 1 in front. So this is actually one coboundary expander, the complete complex. Yeah. Okay, and this co-method actually generalized to a couple other like dense simplicial complexes. Besides complete complex, there's like the k-partite complete complex. You can also prove using this method, and also one can prove the spherical building is coboundary expansion using some clever coloring argument due to Denor and Yotam. And on top of that, also use this co-method. So this is basically one of the more generic way we use to prove coboundary expansion.
Is it in any sense complete? I mean, is this the only way? No. So
if this is complete, then that would say like we probably could not really hope for any constant degree coboundary expansion, because like this I would say this kind of requires the side of triangles to actually. No, I take that back. I'm not sure, but I'm sure. What I'm sure is this method is not complete. Actually, that example, like that example we just saw in like the topological overlapping. This thing is a one-dimensional coboundary expander, but this thing doesn't. We couldn't really apply cone method just because it's too sparse to get any cone around anything, I guess. Oh, actually, no, you can. Right?
To get anything from the cone method, you need to have like constant diameter if you want like constant coboundary expansion, right? Because to have like a small number of triangles, you need even that these paths would be like really, really short.
But
so,
right.
So I guess that you can.
I guess maybe only if you have this, you pick only one of the triangles.
But I think
prove that the number of triangles is proportional to their number.
Right. I mean, if you use it only like this way, where you say that if you're not if you don't agree, then there must exist one triangle inside your cone, then the bound that you get deteriorate with triangles. Of course, you can maybe do things more sophisticated, but I think that like the example that Siqi was drawing on the board, where you tessellate like a huge grid, right? That's what you wanted to do.
Yeah, I think.
So if this is a coboundary expander, then I mean it doesn't even have like short diameter, so you can't expect to get something meaningful from this combination.
I think what Yotam is saying, like if you don't have constant diameter, one can define this correction function globally with a good triangulation, like with a constant triangulation.
Yeah, like you can define it globally, but it's just that like this method won't give you something.
What I meant is if there was an argument saying that the number of triangles in this picture on top, number of triangles is proportional to the number, then this method could prove. Yeah. Okay, let me ask you differently. Is there any other way of proving boundary expansion besides this formula?
I think there are, but probably they're more tailored to the specific construction you have.
But they're different. They don't look like.
They don't look like, at least they don't do correction in this way. Like I think the step of decoding need to be involved everywhere because one need a good approximation for the distance, but the decoding doesn't have to go this way. Yeah.
Sorry. I mean, one way you can try to prove coboundary expansion is to engineer something that looks like something that we know how to do local testability. So like low degree polynomials, we know how to do local testability, right? So you can reverse engineer a complex where the ZI or the BI are something that's a known locally testable code.
Okay. Interesting, but the problem of, I think those codes have good distance.
Right, so you can think of this easier.
Yeah, but could
the whole
possibly.
new direction in coding theory is to find the code distance. And better rate.
No, but your rate is a good rate, but the degree is constant is a good rate.
All right, thanks.
No, actually, there's one more question.
Okay, more questions.
So briefly, what happens if you try to write the analytic definition? Are there for sure no expanders? So if you just try to copy what happens with spectral expanders for say degree 2, for dimension 2.
Okay.
So what actually happens? Because the easy direction a spectral expander is the fact that the spectral expander is an expander, that's the easy direction. So they just don't exist, or it's hard to prove anything, or?
Wait, I'm not exactly sure I get the question. You're saying, are you talking about if we want generalized spectral expansion using the same way that we're talking?
Well, the natural way, instead of F2, write -1 plus an interval, instead of counting do L2 norms.
Okay, I see.
So what happens in the end of this line of thought?
What happens is that at least in bounded degree regime, it's equivalent to the type of high dimension expander Yotam mentioned a couple of weeks back, which is the local spectral expander. And I guess it doesn't have many testing things going on just because you don't have Hamming weight and you don't have cut indicators and stuff like that. But we actually understand that case more.
In terms of explicit, or at least showing that there is a randomized construction.
Yeah, it's easier.
Degree.
Yeah,
but we still don't know that even in that regime. Or...
No, they exist.
No, they exist. Yeah, actually, they all exist. Like if we replace F2 with R, for example, they exist, and They're the run like LSP complies the KO construction, there are all such things, and there are even like more combinatorial, like a graph product type of constructions that actually give that.
The problem that the R definition is not stronger than the F2 definition, unlike.
They're just, I think they're not quite comparable. Like, I don't think that either of them is stronger
In
than
the
the
graph
other.
case, the R definition is stronger.
In the graph case is the same, like it's the edge expansion and the spectral expansion. So because of Chigger's inequality, they're roughly.
Yeah, there's no
It's
Chigger
the
here.
easy, but we need the easy direction of Chigger.
Yeah, but
You don't
neither
have
direction
the-
holds.
And is it possible to write a different analytic definition that's stronger and has this property?
I mean, I challenge you to.
Nice. But then those have other applications, right? The
Yeah.
spectral ones have the samplers and all these other things.
Yeah, an agreement test, yeah,
But they
yeah.
don't get the overlap, so
No,
there's
no.
all the different applications.
Right. Yeah,
Thanks.
thank you.
More question? Okay, great, thanks.